Hello, everyone. My name is Yujie, and currently I'm working as a lecturer and program co-leader of Transport Research Center at the University of Technology, Sydney. And today I'm going to talk about the behavior of granular waste medium with rubber particles under cyclic loading for transport infrastructure. And to start with, I'd like to share with you some environmental issues of Australia. The first thing is about the waste tears. Every year, over 50 million of waste tears are generated in Australia, but the recycling rate is only 13%. So the left waste tears are just piling like mountains, occupying large amount of land, and if catch fire, they can burn for months, which causes severe air pollution. Well, apart from the waste tears, Australia also has a big issue of the mining waste. And every year, millions of tons of mining waste are generated. That includes steel slag and coal ash. So how to deal with these waste materials? Well, in my research, I developed a synthetic energy absorbing layer for sun ballast by mixing steel slag, coal ash, and rubber crumbs together. And here we call it a seal. Generally, these three waste materials can't be used individually because of their adverse geotechnical properties, like the swelling of steel slag, particle breakage of coal ash, and the low shear strength of rubber particles. But if they were mixed with the proper ratio, their adverse geotechnical properties can be balanced very well. For example, in the mixture, steel slag plus the coal ash can provide the shear strength, while coal ash can reduce the swelling of steel slag, while the addition of rubber can further reduce the particle breakage of coal ash and the swelling of steel slag, and increase the permeability, and at the same time, increase the energy absorbing property of the whole mixture. And this will then further reduce the particle breakage of the ballast. And to better understand the dynamic loading behavior of the mixtures, I did a small-scale cyclic track-through test. And generally, for granular materials and cyclic loading, their permanent axial strain can be classified into three categories. And the first one is plastic shakedown. As you can see, this is range A. As you can see, the axial strain of the materials stabilize at a certain cycle. And the good indicator is that the axial strain rate is less than 10 to the power minus 8 by the end of the test, which is 50,000 cycles. And then the range B, which is a plastic creep, which has a permanent axial strain rate between 10 to the power minus 8 to 10 to the power minus 7 by the end of the test. And then for the range C, which is incremental collapse, which has a permanent strain rate larger than 10 to the power minus 7 by the end of the test. And for the waste mixtures, we found there were two governing parameters. The first one is the rubber content, and the second one is vertical cyclic stress. And under low vertical cyclic stress, and here which is 16 kilopascal, as you can see, all the mixtures can attain the plastic shakedown. While when the divisor cyclic stress has increased to 64 to 112 kilopascal, only the specimens with 0 and 10% rubber can attain the plastic shakedown, while others attain the plastic creep. Because the limited rubber content and limited vertical stress, so we didn't find any incremental collapse for the mixtures. But what will happen if we keep increasing the rubber content and keep increasing the vertical cyclic stress? What will happen? To answer this question, we developed an experimental model to predict the permanent axial strain rate of the mixtures. And based on the prediction, we found that under the load, under vertical load, which is 166 kilopascal, and this is equivalent to a 30-ton axial load. And we found when the rubber content is around 62%, and then the mixture will collapse. And interestingly, we also found that if we keep the rubber content less than 15%, the mixture will attempt plastic shakedown under the 30-ton axle load. So if we run the train with 30-ton axle load, it's better to keep the rubber content less than 50%. And to examine what's the track performance with the seal mixture, I also did a large-scale physical model using the track process simulation apparatus, which is currently located at UTS. And in the test chamber, we have 3 layers, as you can see here. So the ballast layer is on top, and then below it is the seal layer, or the traditional ballast. And then below it is the structure field. And then on top of the specimen, we placed this concrete sleeper, and surrounding it is the creep ballast. So this is the loading we applied. So the maximum stress, vertical stress is 230 kilopascal, and the loading frequency is 15 Hertz. This is to simulate a train with 25-ton axle load running at 110 kilometer per hour. And this is the process of preparing the specimen. As you can see, for the ballast directly under the sleeper, we have colored it. So this is because after each test, we will take the ballast out and then check the ballast breakage. And here is the settlement and the electrode displacement. As you can see, when we increase more rubber, the settlement is increasing. And when the rock layer is 40% in the seal layer, and the track has a severe settlement and vibration, and the test need to stop around 2,000 cycles. But for the seal layer with 10% rubber, as you can see, the settlement of the whole track is comparable to the traditional track specimen. And then for the lateral displacement, as you can see, this is for the 0% rubber, and this is for the 10% rubber in the seal. As you can see, after we add 10% rubber, there is a significant reduction in the lateral dilation. And then here is 20%, and then 30%, and then 40%. As you can see, there is a fluctuation in the lateral displacement, so which may cause some unstable lateral movement. So this is not good. This is what we don't want to see. Okay, so based on the settlement and the lateral displacement, 10% rubber in the seal is the track specimen with seal having 10% rubber has the best performance. And then to evaluate the ballast degradation, we adopt the ballast breakage index, which is after Indraratna ETL in 2005. And here is the test result. And here, because we separate the ballast layer in 2 layers, the top layer, which is directly under the sleeper, and then the bottom layer, which is just above the seal layer, just above the subballast layer. And then this dotted point, which are the average ballast breakage index. As you can see, for the track with seal having 0% rubber, has the same BBI with the traditional specimen. And then after we add 10% rubber, there is a significant drop. And then we'll add more rubber, that's no significant benefit. And then interestingly, we found when the rubber content is 10% and 0%, the top ballast broke more, as you can see here, which is the same as the traditional ballast or traditional track specimen. This is because this is very easy to understand because the top ballast layer is subject to higher vertical load. That's why it's broke more. Where after, as you can see, when we add 20 or more rubber, the bottom ballast broke more. So why is that? This is because When we add 20 or more rubber in the seal layer, and that layer, the skeleton of that layer is taken by the rubber materials. So it will behave like a rubber. So when we apply the dynamic loading, it will bouncing back, which causes more vibration. And this vibration will cause more ballast breakage for the layer next to it, which is the bottom layer. And to show you this, I have two videos here. The first one is for 10% rubber. As you can see, it's very, very stable. And then the second one is for 40%. You can see it vibrates a lot. And then, yeah, of course, it would cause more ballast breakage at the bottom layer. So adding too much rubber in the layer may not be a good thing. It will cause more vibration. And then the 10% rubber we found is the best, again found is the best because it is very stable and it will reduce the ballast breakage. And in summary, a synthetic energy observing layer seal was developed for the railway ballast by mixing solvents like cool and rubber clumps together. And secondly, the track specimen with seal having 10% rubber had less lateral dilation and ballast breakage and acceptable settlement. Where when too much rubber was included, like 40% rubber, the track tended to fail with severe vibration and settlement. And thanks for your attention.